Hello guys, welcome to Exam List, and in this lecture series we will do the exact proof of Heisenberg's uncertainty principle. So last time we did the uncertainty principle using diffraction experiment, and we proved the relation del x del p is greater than h cross by using diffraction experiment. Well, we didn't get h cross, but we got h. Okay, so let me remind you what we did in our last lecture. So in our last lecture, we found that the multiplication of uncertainty in position and the multiplication of uncertainty in momentum was greater than h. Okay, this is what we found in our diffraction experiment. Now, this is one experiment. There are many other experiments. So consider there is another some experiment, some quantum mechanical experiment where the uncertainty is del x del p is greater than h by 2. Okay, so there can be a third experiment in quantum mechanics where the uncertainty in position and uncertainty in momentum, the product of them is greater than 2h. Okay, and so on. There are so many experiments with different uncertainty product answers. But in quantum mechanics, it was found that the minimum value of uncertainty product, that is the value of the product of uncertainty in position and uncertainty in momentum, is always greater than equals to h cross by 2. It means there can be infinite number of experiment where the product of uncertainty in position and momentum can be greater than h cross, etc. But the product of these two can never be less than this minimum quantity. Okay, that's why this is the most fundamental result of uncertainty principle in quantum mechanics. This was the result that we found in the diffraction experiment. So diffraction experiment follows this result of uncertainty principle, but most concrete uncertainty principle is this, most concrete, that is the product of uncertainty in position and uncertainty in momentum is always greater than equals to h cross by 2. So h cross by 2 is the minimum uncertainty product value. Okay, is the minimum uncertainty product value. There cannot be any quantum mechanical experiment where the product of uncertainty in position and uncertainty in momentum can be less than h cross by 2. This is the meaning of this statement. However, in our diffraction experiment, we got proof of one that only gave us a hint that okay, the uncertainty in position and momentum product is somehow related to the Planck's constant. But in this lecture series, we will prove this result. This the most general result. Okay, this is the most general result that will prove. And quite interestingly, we will prove it without using any experiment. We'll prove it by using simple mathematics and what we know of quantum mechanics. For example, so let me tell you what do we know of quantum mechanics till now. Okay, so till now we studied that quantum mechanics has something called as psi, which is called as the wave function. Agreed. And this wave function satisfies a particular equation which is called as the Schrodinger equation. Agreed. Okay, then what have we studied? Then we studied that psi star psi gives us probability. Okay, psi star psi gives us probability. Agreed. Or you can also write it as mod psi square, and psi is a complex quantity, so mod psi square is always psi star psi. Then we learned, see, in our previous lecture series we had given great intuition behind this, we had given proper intuition behind this, and we also gave intuition behind this particular thing, that is we studied in quantum mechanics that there is an operator x. We don't know what x is. When x acts on psi, it gives us the position. Agreed? There is an operator momentum. Okay, these things were done in the first two lectures. So when momentum operator acts on psi, it gives us the value of momentum p of psi. So let me give you an example. So momentum operator actually looks as this, equals to minus I h cross del by del x. So this is the momentum operator. So let me just remind you how this momentum operator works so nicely. So what is the most simplest wave function? So assume the wave function of a electron free particle, which we found at a e to the power minus I p by h cross x. So this is the wave function for a free particle. Now when you act this operator, or when you act I h cross del by del x on this, what do we get? There will be minus I h cross outside. Even a, which is the normalization constant, will stay outside, and we have del by del x acting on this part, e to the power minus I p by h cross x. So can you tell me the answer? So the value will be, let us evaluate it here. So we have a minus I h cross, okay, with an a, and then the differentiation will bring a minus I by h cross with p. Okay, so what happens? So this normalization constant, okay, if it stays outside, then you see that h cross gets cancelled, and you get the momentum, you get the value of p. Agreed? Have an sign problem, so what you do is take this plus. Okay, so that will simplify things down. So if you take this plus, you'll get p. Okay, so just ignore the normalization constant for the moment. So you see, when you act p on the psi, it gives you momentum. Agreed? So when you act p on psi, it will give you value of momentum, and that value of momentum, as you can see, is already incorporated inside the wave function. So the wave function contains the information for the momentum also. Okay, you get p. Now do you get only p? No, you have these two things outside it. You have a outside it, and you have e to the power I p by h cross x outside. Okay, so what do you understand? So this is my initial wave function psi. So this is what I have taken as psi. So you see that when the operator p acts on the wave function psi, you get what? You get a momentum value p into psi. These things are already discussed. Okay, so let's not waste time. So just know that there is a momentum operator, which when acts on the wave function psi, can give you the value of momentum. So and the value of momentum, that is the information for momentum, is already incorporated inside the psi. Agreed? So this is a known thing in quantum mechanics. What else have we studied? We have also studied the standard deviation. So we learned that the uncertainty in position is given by standard deviation formula, which is equals to root over of the expectation value of x square minus the square of expectation value of x. Okay, this is what we have already studied. And similarly, we have studied what is expectation value of x. The expectation value of x is equals to integration psi star. Okay, put the psi here, put x in between psi star and psi dx. So this is the expectation value of x. Similarly, the expectation value of momentum. How to find the expectation value of momentum? It's very easy. So what you need to do is you write psi star psi and include the momentum operator inside psi star psi. So what is the momentum operator? Minus I h cross del by del x of. Okay, so this is the momentum operator. Just include the momentum operator in between psi star psi. So and this is the expectation value of momentum. So things are very simple. So here we have actually incorporated the position operator. So we also know this and we also know this. Okay, now the most interesting thing here is these all information from the starting to the last, they carry the uncertainty principle. Quite amazing, huh? Just these mathematics, just the value of psi, then this basic definition, just this basic definition can be used to prove that del x del p is greater than h cross by 2. This is the most amazing thing that we'll do in the next lecture. So in the next lecture, we will only use this information, and we will derive this uncertainty principle. So neither I'm using any experiment nor I'm doing any other thing. Agreed? So in the next lecture, we'll derive it.